love that animal. That's good for travel. All right, it's Friday. Microphone is on. Obviously, nobody was expecting me to be the one teaching today. So usually I don't operate on Friday well. So what we're going to do today is to discuss about your next homework. So it's not going to be your regular lecture, sort of. Okay? So it will be lots of things that you have seen them. Of course, when I say you have seen them, I don't imply that you have studied them, you know. Visually looking at things is one thing, studying them is another. So what we want to do is so the next homework is a series of regression cases using the same data set that is referred to as the caterpillar data set. And this homework attempts different priors. Discusses the problems with the different priors, and it addresses variable selection or model selection in the context of regression models. So if you have regression in 10 dimensions, do you need to include all of them, or some are not important, okay? And it does it with two different ways that we have not explicitly discussed before. So one of the ways is using sampling methods, which will come in our course in maybe 2 or 3 lectures down the road. And the other way is using Bayes factors. I mean, you use Bayes factors for some toy problems, comparing model 1 to model 2. How about if model 1 is including 9 input variables versus 10 input variables? Will that make sense? Can we do that? All right, so this homework is, you know, I was wondering if I should just ask you to do it the same way I did ask other students in the past to work on this in 2 weeks. And then I'm getting nervous as I see the audience diminishing exponentially, okay? Well, some of you are laughing, right? But let me just say, unless you figure out what your strengths are and where you can push yourselves, we can basically joke and I can give you a picture, say this is regression, see you next week, life is good. But it won't be fair to you. They pay me lots of money to teach you what I know, and I cannot do anything else. All right, if you don't like it, what's the expression, John? Those are polite ways of putting it, okay? All right. So we were discussing just before I came down what we should do, and so the actual homework. I'm going to give you, of course, the notes. They have all the proofs, and even more importantly, there are 2 different implementations of everything. And don't get excited because I asked the TA to actually grade this harshly, because the expectation from you will be to demonstrate in whatever way you think is appropriate that actually you have control of this material. So we give you the computer codes, we give you the theory, we give you everything, and still we're asking you to find the means to demonstrate in your solutions that actually you understand what's going on. How can you do this? You submit your own code, you submit proofs, you find 50 mistakes that we have, I'm sure there are, any other possible means, okay? If you just say, oh, but there's nothing there, and you try to work on this next Tuesday, and you submit it, we're not going to be very happy, okay? But right now, everything is given, so sleep well. All right, with the sleeping well, I notice the actual reference from this is this book by Roberts, The Bayesian Core, which is a wonderful little book in Bayesian inference. And actually, it doesn't provide, it's not for people new to the area, so you're supposed to know a few things. But every chapter has some new comprehensive concepts in the context of Bayesian inference. And one of these chapters is about regression. So I realize if you hit this, unless it only works on my computer, the whole book, you can download it from Springer Verlag. It works, okay? So that may not be the case. Now, for those who are listening to this tape from overseas, you should be able to download somewhere else and you will find it, all right? So if not, please contact me. Okay. There are lots of slides. We are not going to cover everything since this is your homework problem, right? So obviously this is called the caterpillar problem because it models, I believe, the number of colonies of caterpillars in terms of different input variables. And those input variables, they're what you see here. They have different physical meaning, okay? So this is a 10-dimensional problem, okay? So it is sort of a challenging problem, but 10 dimensions and doing regression, maybe it's challenging in a homework setting, but you will see when you try to implement this that if it is 10 or 25 or 50, it doesn't make any difference. The same program doing all the algebra, okay? But computationally, this will not take you maybe seconds to run. It may take half an hour on your laptop to get all of the results. So what we want is to do regression using different prior models. We want to compare models, and for example, if you have many dimensions, here 10, we need to figure out, do we need all of them? Can we omit a few? And you will see with different methods, we can actually get rid of some of this dimensionality and without affecting any results in the predictions of the response of the system. So we're going to discuss this with sort of two methodologies. I have to repeat this. The algebra looks complicated. It looks complicated because when you convolute simple things, you get complicated formulas. The concepts are easy. I cannot emphasize this more, right? You can, if you think, you say, well, if it is like that, why do you give us the formulas? I give you the formulas because tomorrow, when you try to work this in your research, unless you have learned how to do these hand calculations, you're not going to go anywhere. Nobody's going to do this for you. You have to do it for your own. Okay? So formulas are complicated. You have to do them. If you don't do them, don't tell me you know regression because you don't. So when you read the homework, right, and the chapter, basically, I want you to reproduce, well, it's already there, but I want you to, convince me that you can reproduce all the results. And the first picture is to plot, basically, this 9 of these inputs versus the outputs. These are the given data. And I believe y is on a log scale, and x is, basically you have to, plot them in a way that you can see the relevance of each dimension on the response. And looking at these pictures, it's very hard to say, for example, that you don't really need, let's say, x4 or x5 or something, because, I'm looking visually, and it seems to me y depends on everything, all right? But of course, some of this input information may be correlated with other input information. At the end of the day, it doesn't provide anything. For example, it's very possible x5 and x1 together may be giving you the same information as x1 alone, but we don't really know this a priori. All right. And again, don't get excited, okay? I give you the codes. If the codes don't work because the MATLAB version is a little bit old, don't call me and say, oh, it doesn't work. You make it to work. And when you read both codes, you realize, these are from two different students, that they have not only programmed this nicely in an optimized code, but they also have found about 50 mistakes in the book from where we got this. And those mistakes required heavy-duty calculations, so they have put the effort to actually figure out those mistakes. Okay? And it's very possible there are additional mistakes that we have not located. So, a little bit of a technical warning, right? When you talk to statisticians, even the ones that do Bayesian inference, like in this book on Bayesian core, some of the calculations, they're non-Bayesian, okay? But they're so common in the context of regression that I decided to leave them on in this homework assignment because it's not, it's a good idea to know what results may people expect you to do, even if they're not Bayesian, okay? So I'm going to emphasize where things really are not Bayesian, but are expected in the context of regression models. So that would be a good departure. All right, so we have our data, n data, y is the output, okay, y1 to yn, y is scalar in this problem, and this is our design metrics, and in this textbook, the design metrics instead of phi that we use is denoted with capital X, okay? So we have k variables, and you notice we put the bias term here like that, so in reality we have k plus 1, so basically the size of this design matrix is n times k plus 1. All right, so the regression model looks exactly what we have done. That's standard in Bayesian regression. We have an additive noise with variance sigma square, which is not known, and the mean, that's our regression function, is x times beta. Okay? So it's a linear regression problem. Notation-wise, again, I did not want to go and change the notation from the textbook because then we will mess things here and there and we will not be able to compare formulas visually. So beta is what it used to be our W in our regression model. Okay, so please take a note of this, that our regression model is given as the parameters are beta, and the design matrix is capital X. There's no way you can miss it when you follow the analysis, but usually, beta we affiliate with some parameters in the model, so they're still the parameters, but they're the regression coefficients. Okay, so so this is our regression function, right? So the mean of, if I have beta and my training data, so the mean response is basically this linear regression function, and the noise is sigma squared. Okay. You guys will read this. Okay, so let me. All right, so you will, obviously this matrix X, the design matrix, is not invertible, and generally we are going to assume that we have more data than k plus 1, right? Otherwise we're going to be in trouble. So we assume in the remaining actually of these slides and in the homework that the rank of X is k plus 1, okay? And that implies basically that X transpose X is invertible, so we can actually write the maximum likelihood estimates exactly as we did before. But keep in mind that this number k plus 1, so we use k plus 1 input variables including the bias term here. So likelihood, exactly as before, there's nothing new. By now, you should look at this expression and say it's boring, Okay? So the next slide, I'm going to show you the MLE estimate, and I'm going to show you some trivial calculations that are non-Bayesian, all right, but very common in the context of regression. So the maximum likelihood estimate, let's concentrate only on the top, right? We already have discussed this. You take derivatives with respect to b. So beta hat is the maximum likelihood estimate for the parameters, the regression coefficients. Don't read the whole slide, okay? We agree? This is exactly as before. There's nothing new there. Yes? All right. It's Friday. You have to give me lots of yes, you know, so I can have energy to keep going on the weekend while preparing the lectures for next week. So this is the MLE estimate. Now, the Bayesian way will accept basically this as a point estimate, and that's the end of the story. Right? There is a point estimate, that's the end of the story. The non-Bayesian people will actually affiliate some randomness in this estimate, and that randomness will come from where? Look at this equation here, right? And where is possibly this randomness comes? Where? Beta, you say? Delta? Y. All right, Y. Okay. So let me. So when we do a Bayesian analysis, right, we provide the design matrix X, this is the input, Y is the output. A fixed data set, that's it. We don't have any more data. There's nothing else. We need to make an inference using only the data X and Y. The non-Bayesian people actually, they say Y is a sample coming from our data distribution. So Y is, in essence, if I sample some other points, there would be different Y, and as a result, there would be a different MLE estimate. So there is randomness in the MLE estimate. I emphasize non-Bayesian, okay? But I think this assignment is good to tell you a little bit about the non-Bayesian way. So beta is really random for the frequentist because Y is random, and Y obviously we know it follows a Gaussian distribution that looks like that, right? That's our likelihood model. So if that is the case, looking here that this MLE estimate is a linear function of Y and Y is like that, will you agree with me? Look now how this equation became complicated. Will you agree with me that now beta hat follows a Gaussian distribution that looks like this? I mean, the relation between the MLE estimate and Y is linear, right? So the mean will be this coefficient there, X transpose X minus 1, X transpose times, X beta, okay? And the variance, you have, you remember for linear systems, right? You have to put the matrix transpose and the matrix again on the right-hand side, all right? So the variance will look like that. Yes? All right. So the MLE estimate comes for the frequentist to be a Gaussian that has a mean the exact beta, okay? And it has a variance that is sigma squared X transpose X minus 1. So this is really absolutely non-Bayesian, right? So basically you can say, yes, the mean of that is equal to beta, which we already know that has to be the case anyways, but now it affiliates a variance that we did not have in this estimate in the context of Bayesian analysis. So if somebody asks you to compute the variance on the MLE estimate, really they are talking in a non-frequentist manner, accounting for the variability in the data Y, and that gives you a variance of the sigma squared X transpose X minus 1. Okay, non-Bayesian. I want to emphasize non-Bayesian, but when you have to compute error bars on this estimate, these error bars will be plus minus the square root of this variance. Okay. Now, All the derivations are in the notes, and there is some very interesting things that I want you to read them, all right? But I'm going to give you the conclusions, and you read the rest of the analysis, okay? If you take the derivative with respect to sigma squared, you get the MLE estimate that looks like that. Correct? Yes. All right. So nothing new there. As you expect, basically, this MLE estimate is not unbiased. All right. So basically, you know, the mean of that, if you vary your data sets, is not going to be the sigma squared from your data set. Okay. So we will need to correct this. And so the question is, and the calculations are in the slides, and you should read them. That is going to be good for you, is can we compute what the mean of this is and what the variance of that is, and then maybe define an unbiased estimate. So the calculations are in the slides. They look a little bit messy because our design matrix is not square matrix, right? Has rank, as we said, k plus 1. And when you do the calculations, here what you get. You get that the expectation of that MLE estimate is sigma squared over n times n minus k minus 1. That may look sort of new to you because we have not given this calculation before, all right? Okay, so you remember how the corresponding formula for a Gaussian looks like? You know, if we were doing an MLE estimate for the variance of a Gaussian, how will this formula look like? Sigma squared over n times n minus 1. Here it comes n minus k minus 1, all right? So here is our new result, and that's why I did not put a hat on that. The actual unbiased estimator for sigma squared is basically y minus x beta hat, where this is the MLE estimate, divided by 1 minus k minus 1, okay? Where s squared is given by that, okay? So the unbiased estimate for the variance for the noise sigma squared is basically this, okay? As a matter of fact, in your assignment, this is what you will have to use when you do point calculations. You are not going to use this sigma squared MLE. This is the actual unbiased estimate that you will need to use, and it's n minus k minus 1. Okay? Now, so basically on the bottom it says here, you know, you remember we said that the MLE estimate for beta for the coefficients, this is the variance. So obviously this is the exact variance, which you don't know. So when you approximate the variance in beta to plot error bars on the MLE estimate of beta, you basically have to use this unbiased estimate, MLE estimate of sigma squared, okay? So here there is sigma squared hat. So the notation here, it's important, right? This is not the MLE, this is the unbiased version of the MLE that looks like that. All right. Okay, here are some proofs that you need to do this derivation. Let me put all of these things up. All right, come on. Okay, so a little bit of more taste of frequentist statistics. If you use this unbiased estimate of the variance, okay, then you can define what's called the standard t statistic, okay, which involves this MLE estimate of beta for each of these coefficients minus the actual beta, and this comes out to follow a student t distribution with n minus k minus 1 degrees of freedom, and this omega ii is basically the diagonal elements of the variance that we had for the parameters beta. So basically what, you know, so the t statistic is defined like that. If you search on Wikipedia, you can read about that this t statistic follows a student t distribution. The point here is that somehow you can use this for hypothesis testing, and lots of frequentists basically use this for hypothesis testing. So let me give you one example of hypothesis testing that you will have to compute in your homework. One of these hypothesis testing is to compute what is called the p-value. And the p-value is sort of the most murky, stupid sort of concept in frequentist statistics, that if you ask statisticians to explain to you, they will actually not manage to do so, okay? Because it doesn't mean much, okay? You know, if you search in life sciences, biology, etc., all the journals are bombarded with p-values because they expect you, when you do play with experimental data, to record those. But again, in a Bayesian setting, they are sort of not acceptable. But let me tell you what the idea is. Let's suppose that the hypothesis H0 is that one of the coefficients beta I equal to 0. So this is an important problem, right? If beta I equal to 0 means that the I input direction is not important. So we want to check that hypothesis versus non-H0, which means, yes, we need I. The I. So remember on these formulas that we had before on the T statistic, right? Where was it? No, on the previous slide. So here, this is the I regression coefficient. So if that is 0, means we don't need the I dimension. So the hypothesis H0 is one where this beta I is equal to 0. And this p-value that is going to help us to make a conclusion if the I direction is important or not is to compare basically the T statistic, which I was given on the previous slide, with this value that you see here, and I'm giving you the explicit calculation, all right? Since the distribution of this T statistic is a student T distribution, you can actually compute this exactly, and I'm indicating here the calculation that goes in the actual computer program, all right? So you're going to have to use the CDF of the T distribution. And the p-value, if it happens to be less than alpha, so what do you do to the hypothesis H0? Anybody knows these things? Huh? You dismiss it. So this can be a useful trick to figure out if you keep the I input or not in your computer code. Okay, so I think I'm going to show you this on the results. All right. So this is one of the tables that you're supposed to program. The whole program basically takes a few lines because what you have to do is compute this the MLE estimates, one formula, compute the error bars on the MLE estimate, another formula, compute the T statistic, another formula, and then compute this T value using basically the CDF of the student T distribution. And notice here I have marked effectively these p-values that they are smaller than 0.05. And being smaller means we have to reject what hypothesis? What was the H0 hypothesis? That the coefficient I was not needed. So what that immediately tells you that the intercept very important, the first x1 very important, x2 very important, maybe x3 not so important, but x4 and x5 very important, and the rest basically you can just get rid of them. Okay? So again, you talk about model selection, right? The frequentists have a way to do model selection, and it's not going to hurt you if you read a little about the p-values and understand this calculation, which is, I have written explicitly in the slides, the formula, and then, basically appreciate the fact what it means that the hypothesis here is rejected. So basically beta I is supposed to be there. All right, so the stars mean for certain this is a very small number, so the intercept is needed, x1 is needed very much. 1 star means a little bit less. The rest, basically, you can get rid of them. All right. So let's continue. I'm I'm sure very soon I'm going to start clicking things, but since this is your homework, you can go and read the rest on your own. So the likelihood calculation, we just wrote it before. We have two unknowns, right? The coefficients, beta, and the noise sigma square. So what I'm doing here is, and we already have seen this formula, it's standard when you play with Gaussians and additive noise. So I have rewritten the likelihood where I inserted in the calculation the MLE estimate of beta. We have seen exactly this formula a few times, okay? So S squared is the error of the regression model makes in the predictions Y, okay? Beta hat is the MLE estimate, and this is an exact expression, all right? So the likelihood looks like this. Obviously, I'm going to make some use of this. Actually, the results in the next few slides are, things we already have seen here and there. So we're going to assume a conjugate prior, and you remember it has to be a normal inverse gamma type of distribution. So beta given sigma squared is a Gaussian with unknown parameters. The scarcity beta is not beta hat, okay? So remember, the scarcity beta comes in the prior model. There is a matrix M that is also coming in the prior model for beta given sigma squared, and sigma squared is an inverse gamma distribution with parameters A and B, okay? So obviously, you can select different values for this scarcity beta and M, and for the coefficients A and B. And when you play with the homework, you will see that your choices can make a huge difference in the type of results that you get. So you have to be very careful. So the posterior, you multiply the likelihood times these two priors together. We already have done the calculations, and you get this very complicated expression. Remember, simple formulas give you long expressions. If you type them by hand, the chances that you will miss 50 of these terms, or that you will confuse beta hat with curly beta, are about 99.9%. So typing builds character, right? Typing builds character, okay? From this joint posterior, you can get actually the posterior of beta given sigma squared. Can you tell me actually, without looking at the calculations, if I give you this posterior, how do you get the posterior of beta given sigma squared? What do you have to do? On the equation on the top, if I want the conditional posterior of beta given sigma squared, what do you do? So basically, you treat sigma squared as constant, all right? And you put all the terms that involve beta together, hoping that some nice distribution is going to come up. And because this is a conjugate prior, it better be a Gaussian, all right? And indeed, it comes out that the posterior of beta given sigma squared, it is a nice Gaussian that has this nice mean, all right, this nice mean, and this variance. Okay, so I remind you, the mean involves here, it's a combination, basically a convex of the, combination of the prior mean, right, that's the curly beta, and this is the MLE estimate, okay? So that's from where this thing is coming from, okay? You can, now, to compute this marginal posterior of sigma squared, you're going to have to integrate beta completely out, all right? And that requires basically that you use the Woodbury formula, you find the normalization factor for a Gaussian, etc. But it is really, whatever way you do it, if you know that you need to get rid of beta, all right? And the only way to get rid of beta is to get an integral that is the normalization of some Gaussian. So if you do the algebra, it comes out with some goodwill that the marginal is an inverse gamma distribution that is given by this nice formula, which we have seen it before in all the slides. There's nothing new there. It's the exact same formula we discussed before. Okay? So an inverse gamma distribution, remember the prior had only alphas and betas. Now we have alpha plus n over 2 and beta plus all of these terms that involves this error in the data and the predictions of y, plus actually this nice term that contains effectively both the mean of the prior and the MLE estimate of beta. So the marginal posterior, this is very important, the marginal posterior, there's no beta here, is, you know, I'm giving you the formulas for inverse gamma. You can see that you don't have to memorize this. The mean of an inverse gamma distribution is beta divided by alpha minus 1. So this has, you know, beta is this divided by this minus 1. You get this nice expression for the marginal posterior. Okay? So the marginal posterior of sigma squared is given like that. So you're going to have to, you know, plug in some particular cases that are more popular in practice. And one of them is to assume for a matrix M to be the identity matrix divided by some positive constant sigma, and take the mean in the prior model to be 0. And then it comes out that the, let's see, when we plug in this nice formula here, it comes out that the conditional expectation of beta is given by this nice expression, and this fits under what is people in statistics call rich regression models. Okay, so for us it's just a very particular case of using a prior model with this matrix M, and it looks like that. Okay, and again, rich regression is nothing else but basically regularized least squares, right? Because this is your normal regression models, and then you add a regularizing term, basically I over sigma. Okay. So now in this formula here, this is the expectation of beta given sigma squared, and somebody will tell you, I don't like this, all right? Because sigma squared is not known, so this is not very helpful. So really what you will need is, you will need to find this distribution, all right? Get rid of sigma squared, and how do you get rid of sigma squared is by integrating this with a posterior of sigma squared out. And this is the calculation that you see on the top. And if you do the algebra that's in the slides, this is what you get. This is a nice formula. Again, simple formulas give you very complicated answers, eventually leading to simple formulas. So the posterior marginal of beta is a student t distribution with k plus 1 dimensionality and n plus 2a degrees of freedom. The mean and the variance basically are given in these lengthy formulas that you see on the bottom. Okay? Again, you will say, wow, this is a simple regression, linear regression problem, and I get the posterior of the coefficients looking like this. Yes, that's how they look like. But, I mean, it's just, you know, this is what you get, right? And it's a nice closed form solution, so you should feel blessed that you have an analytical expression rather than having to numerically sort of do this type of estimations. So if you have this posterior as a student t distribution, effectively what you can do is you can look at the tables for the mean and the variance of that. And so, you know, if you, you know, you can write directly what the mean of beta is and what the variance of beta is as well. All right. Another calculation that is going to come, because you're going to have to do predictions, is the following. You will need to predict, so you train your model, let's say, with data x and y, and somebody gives you a new input x, curly x, and it tells you, tell me what the output is. All right? And I do this in two steps. In the first step, I calculate the predicted distribution given sigma square, and then once I get this result, I'm going to integrate sigma square out. Okay? So we're going to do this in two steps. One step is we're going to calculate, again, the predicted distribution given sigma square, and another one to integrate sigma square out. Okay? So if you try to calculate a predictive distribution given sigma square, you have to bring beta back because the likelihood models involves beta. So you have to do this integral. So what is the first term in this integral? What is the first term that I see there? How you remember the predictive distribution, how it looks like? So what is this first term? That's the likelihood, right? If I knew beta and sigma squared and I have my new input, so basically, this is a Gaussian, right? And then what will you need? Of course, you will need a posterior, and because we condition everything on sigma squared, the posterior is also a Gaussian. So this is, this marginalization will also give you a Gaussian. So the y hat will come to be a Gaussian, and you can do the calculations, by taking this product explicitly, closing the square, and then coming up with the mean and the variance of curly y. There is another way that I think it's given on the next slide. If not, I will show it to you later on. Yes. All right. So look at this. Okay. We agree. Let's see how we're going to do this. We agree that this is Gaussian, this is Gaussian. So the product is a Gaussian. If we marginalize, we get a Gaussian. All right. So are you going to be happy if instead of closing the square and spending 1 hour doing the algebra, if actually you can compute in a few minutes the mean and the variance of that, and then say, here's the Gaussian? Right? So statisticians, by the way, they like this. They don't like, they have learned all the tricks on earth, right? So here's the tricks. You only have to see the formulas on the top, and I want you to read the rest in your slides. Let's look at the first equation. Tell me what it says. So if you want to find the expectation of x given z, this is the expectation given z of the expectation of x given something else in z. So this expectation is with respect to what distribution? Can you tell me? This inside expectation, I'm taking the expectation of x, cannot be with respect to y. This inside expectation is the expectation with respect to what distribution? X given y and z. All right? And once you do this expectation x, you get rid of it. All right? So obviously the result given z is going to be a function of y. So the first expectation is with respect to what variable? To y given z. All right? And the proof is basically given here. And this is actually this two expectation inequalities are extremely important, especially for variance calculations, not as much for the mean, but the second. So the variance of x and z is the variance of this conditional expectation and the expectation of the conditional variance. Extremely important formulas in calculations, okay? So why do we care? Because let me show you. I'm not going to go through the algebra, but if you want to find the expectation of curly y of our predictions given sigma square, you know what I can do is I can bring beta in the picture and say this is the expectation of y curly given beta and the rest of the things conditioned there. So I bring beta in the picture. And why do I bring beta? Because can you tell me what's the expectation of curly y given beta and the rest of the things? So if you knew the regression coefficients, what's the expectation of curly y given beta? X times is the x curly, right? That's my input corresponding y times beta. And then you can move this thing outside, and what is the conditional expectation of beta given sigma squared? We computed before. You do the same thing for the variance, and there is the nice answers. No closing the square, no nothing. In a few seconds, you have the conditional. Basically, you have a Gaussian that represents the conditional predictive distribution, and conditional because I'm taking sigma squared to be given. But as I mentioned to you, we will also integrate sigma squared out. And there is the answer. You do all these tricks, by the way. I am doing them multiple times on the slides. So if you integrate sigma squared out, all right, so you put the posterior of sigma squared, you have a huge integral to deal with, 2 slides, 3 slides, and here's the answer. The predicted distribution, curly Y, is the student T distribution that you see here. So basically, no beta, no sigma squared, nothing. All of these weird parameters, including the regression coefficients, are out of the picture. And now once you train the model for any input, you can say what the output is by plugging in, and you know the uncertainties on the output. Nice. It doesn't make a sense to say the predicted distribution given all these parameters. I mean, if those parameters are random, that's not a useful information. But here, there's nothing random, all right? I mean, no betas, no coefficients, no sigma square. This is the predicted distribution, and it comes out to be a very nice, student T distribution that is given by this wonderful formula. This formula not only has taken some time to type, but some time to derive and convince myself that is actually correct. All right, so hopefully you can do the same thing. So if you go back to this particular prior that we usually implement for each regression, and you put m equal to I over sigma, and the prior mean to be equal to 0, I'm going to show you how the examples look like. All right. So remember now, in my prior for the conditional prior beta given sigma squared, the m I put it as I divided by c. Okay. So there is a coefficient c there that I say can be any positive number. So let's see what happens when you play. So these are the results. This is the posterior mean of sigma squared. This is, I am only showing here the beta 0. This is the bias term. This is the mean of the bias term beta 0, and then the variance of beta 0. And what I have done is I changed the coefficient c on my prior, and I'm showing you results for different priors. So look at these numbers and tell me, are you happy with sort of this Bayesian analysis? How do the results look like? So as I change this thing on my prior, what is happening? These numbers, I mean, you can see here, like the mean goes from 0.12 to 10. Can you imagine if you, let's say if this you represent it with a straight line, and somebody tells you the intercept is 0.12, and somebody else comes and says, no, I did, Bayesian thing, the intercept is 10, day and night. All right, so immediately tells you that this concept of ridge regression and plugging in some coefficient c, it's actually very, very sensitive on what your choice of c is. Okay, so you have to be extremely careful with that. So if you take c equal to 100, what actually you can do is you can plot the mean of the coefficients, you can plot the variance, and actually somewhere there you can plot the Bayes factors. I'm going to come back to it, right, for model selection, but right now you have the mean and the variance of the coefficients and other nice good things. Okay, I have to go faster now. Okay, we're slide 41, and so I'm going to keep clicking. Okay. So the idea is here we need a more sophisticated prior, and particularly a non-informative prior, right? Not necessarily this nice conjugate prior that we had before. So this prior, we already have seen it, and here it is. It is what is called the informative G prior that looks in this nice form. So there is still a coefficient C. The posterior of the prior of sigma square, it's a Jeffreys prior, 1 over sigma square, and beta given sigma square is a Gaussian. Okay, and we already discussed that this is really anti-Bayesian because the variance, the covariance matrix in this conditional prior model depends on the data X, right? This is unacceptable, all right? So a Bayesian person would tell you this is, this is a no-go, but you will see by doing this, the results look actually very stabilized and less sensitive to this coefficient C. Okay, so obviously, if you're going to use this prior, means you're going to have to repeat all the algebra from before from scratch. Like new posteriors, new marginal posteriors, new predictive distributions, everything from scratch, because now having this covariance there is going to affect your calculations, but it's really sort of algebra at the end of the day, okay? And you can see here, where is it? I miss it. It says, even when you do that, unfortunately, there is still strong influence on C. So even this, as it is, will not be ideal actually for what we want to do. So the results are in the slides. This is the conditional posterior of beta. Okay. This is the posterior of sigma squared, okay, with beta integrated out. So this is the marginal posterior of sigma squared. This is the actual posterior of beta with sigma squared integrated out completely. It's a student t distribution. I mean, if you look, there are similarities with what we had before, but also there are big differences because of the of this term, effectively. In the context of the regression coefficients, if you know the posterior of beta with sigma squared integrated out, you can actually do calculations of the mean. And this actually, and I think this is the reason people like this G prior, you notice the posterior mean comes to be a simple linear interpolation averaging between the MLE estimate beta hat and this beta mean in the prior, okay? And the averaging is with the coefficient C. So it sort of has very appealing form. And from this, you can extract from the generic formulas, you can extract what the variance in B is. Okay? I mean, you can see here if C equal to 1, all right? And this is why you should be concerned. If you select C equal to 1, this formula tells you that the mean in the prior has the same weight as your MLE estimate. You see that? If C equal to 1, basically in the estimation of the posterior mean of beta, it comes out that the MLE estimate has the same weight as the mean of the prior. That's unacceptable. I mean, can you imagine you go and collect lots of data, and then somebody tells you the mean has the same role as this beta curly, right? The same role as all the data you collected. It doesn't make a lot of sense. What happened to your neighbor? We miss your neighbor. There was somebody next to you, that's why I'm commenting. So I turn my head for 2 seconds, people leave the room. In this country, by the way, for those listening from overseas, professors don't get much respect from their students, okay? So professors turn their backs and students disappear. Unfortunately, they did not hear you on the tape, so, and I'm not going to repeat it, okay? So, all right. So you can complete all these calculations. So let me just show you what you get, right? So if you take some given C, this is the mean that you get for this regression coefficients. This is the variance from those formulas that I repeat them again. And actually, I want to spend some time to hypothesize. I'm not going to give you the algebra. It's on the slides further down the road. This is the biggest factors. And I want you to tell me these biggest factors, what are they? I mean, I am listing there log 10 of biggest factors corresponding to each of the input variables. So what are those variables? I mean, what are those biggest factors here in this context? Can you guess? I mentioned it in the beginning of the lecture. So how do we compute this? What do they mean? What are they? I don't want the details of the algebra, right? But obviously there is one biggest factor for each of these coefficients for the intercept, input 1, 2. So what exactly are those? You remember the biggest factors is a ratio of what? Of 2? For those two models, the way we define it, we take the ratio of the likelihood, of the marginal likelihood. So the way that you see this, obviously these are ratios of likelihoods, okay? So what is, I'm looking on this number, 2.1873, the ratio of which two likelihoods? What are the two models? When I put this next to the intercept, I say, here's the biggest factor. So it's the ratio of which two likelihoods? Say it again? Exactly. So it is the ratio basically of the likelihood corresponding to the full model where everything is in, and to the model where, let's say, for this number 2.1873, you don't have the intercept term. So basically, once you have your marginal likelihood for this, what you need to do is go in your input data and get rid, the variable that corresponds to the intercept, right, in your design matrix X, and you repeat the marginal likelihood calculation, and the ratio of the two likelihoods will give you the biggest factors. This is a fantastic way, actually, to see these biggest factors in action in the context of model selection, effectively, or basis function selection, or input variable selection. So obviously, I see this a number that is higher than 1. All right, this is log 10, by the way, so it's a big number. And I see 4 stars here. What does that mean? So this variable, very important. This variable 1, very important. This variable x2, very important. This negative, not good for you. This smaller, but maybe important. This important, the rest not important. And by accident, by the way, when you compare this with the p-values, it comes, more or less the p-values gave you the same answer as well. All right? But this is fully Bayesian. All right? This is fully Bayesian, so this is a nice way to do this. Okay. I am, so you guys read the rest, I even compute, high density intervals for the posteriors of the parameters, these are very important actually, because, for example, right, these intervals, when you compute them for the posterior of these parameters, you know what? They can also tell you if these parameters are important or not. How is that? So they can be used also for selection of input variables. How do you think that may happen? Like if I see a parameter and has an HPD interval that does not include 0, what does that imply to you? That variable has to be there, right? So you can see B0 is all positive, all right? Beta 1 is all negative. But now you go to beta 6, for example, -3 to 2. Like, good luck, right? It's like this, can be like this way, can be that way, doesn't matter, means it's not important. And the same thing for the other variables. So keep in mind, when you do model selection, this probability, this high density probability intervals for the posteriors can be used effectively to do model selection as well, okay? And so a very nice way to do model selection. Okay, keep going and going and going. And this is this biggest factor that I mentioned to you before, okay? So we have the, when you do the analysis, right, you compute the marginal, the likelihood basically for the models. This is the likelihood where every basis function is included on the denominator, and this is the likelihood where you have removed one of the basis function at a time. So the ratio of the two, it's a very nice formula. You just write a nice computer code, 2 lines. you know, and but you write a code where symbols mean something, all right? Symbols mean something, okay? So symbols mean something, and when you do this, you get the nice Bayes factors. And actually, you know, how do you do this, you know, for every input variable? Well, you know what? You can put this in a nice loop, and I copy this from one of the students who programmed this. Look at this, how simple things, right? He makes a loop on the basis functions j, and it says, you know what? Go and start subtracting from x, basically, one of the input variables at a time, and define this new input x0, this new design matrix x0, that includes all but j. One line. Okay? So nothing, no headaches, no nothing, you know, and one formula and another formula can give you all the Bayes factors that you need for all the variables. Okay, you know what? Let me, so I mentioned that this Zellner's prior with a given coefficient c is still basically not very robust to different values of c, okay? So here is the proposed way from the reference I gave you. Well, make c, that coefficient c, a random variable as well. Use a hierarchical Bayesian formulation effectively. So make, what happened? What slide was it? Okay, here it is, thank you. So, so basically, beta is not a problem, you take the mean to be 0, all right? But it introduced basically a uniform prior on C over some interval, okay? So the prior on C will look on an interval, let's say, of you know, size C is 1 over C, okay? So that's the, you know, a diffuse prior for the coefficient C. I remind you, C was coming in our prior model in the Gaussian that was defining the beta distribution given sigma square, okay? So we're going to take that C to be a random variable and come with some prior model that will look like that. So effectively what you need to do, right, hierarchical models to produce the posterior of beta and sigma square without sigma at all. What I'm going to do is I'm going to use the posterior that we had in the earlier slides given sigma times the posterior of sigma. Look at that formula. I mean, this is classical, basically mixture model for hierarchical Bayesian models. You plug in another variable, okay? You know how to write the posterior of beta and sigma square for a given sigma, because that's the standard analysis that we have seen even in earlier lecture. But now I'm going to average with respect to the posterior of sigma. There's no other variables here except my data. And what's the posterior of sigma? Is if I use Bayes' rule, is the likelihood of y given sigma times p of sigma divided by this term here that doesn't have any c. So it's a normalization constant, so it's no value. So we know this, it's 1 over sigma. Can you compute for me the marginal likelihood of y given c? How will you, what type of calculations will you need to do to compute this term? Or, you know, do we have an answer to this? Do we not, I mean, if you do a Zellner's prior analysis, like in the previous slides, if I keep going backwards, should we have somewhere this term, you think? That's the marginal likelihood for using a prior with some coefficient c. It better be there, right? It's a classical, you know, that's the likelihood. So effectively, if you plug in the expression that we had from before, this averages over all possible posterior values of C. And this comes, even though this looks an infinite sum over C, it's really the sum converges very rapidly, okay, when you look at the calculations. And this C has no direct effect, but introduces robustness in the predictions that the Zellner's prior alone cannot do, okay? So this is a little trick, a neat application of hierarchical Bayesian analysis again, where you remove the effect of one of the parameters by treating it as a hyperparameter and putting a prior on that, and then basically integrating it out. Okay. The results actually, they are, I'm giving you all the results in the notes, you know, and the estimate of beta, this is the posterior mean, for this new prior comes to be the ratio of these two sums that you see here, all right? Again, the good news is they converge very fast, okay? There is no prior mean here. I took it to be equal to 0, all right? So we set it equal to 0. So this is the MLE estimate, and you can get the variance, you can do anything you want to, and I give you the results, and the results actually look very stable and much better than having to select this regression coefficient C, okay? So, and you can compute the Bayes factors again and again. The only thing you have to do is, you know, change the formulas for the mean of the variance of B and the Bayes calculation, and the formulas only change because this marginal likelihood change a little bit. Okay, so, all right, so let me finish. I have 10 minutes, and this is extremely important. It's a little bit ahead of us, but it tells you that we can be futuristic, all right? So we have K input variables, and we discuss the Bayes factors, the HPD intervals, you know, different ways, the p-values, to decide which of these variables are important. So I'm going to use ideas from Monte Carlo methods to do this selection of input variables. We haven't formally discussed Monte Carlo, right? But you did calculate integrals with Monte Carlo now, but I'm going to tell you a simple sampling method that may be able to address this problem of variable selection in a very nice, cute way. Okay, so we cannot really wait to do the Monte Carlo methods and then come back to these regression problems, because by then regression is history for you, right? So we need to do it now. Okay, so let's assume the following thing. We have these variables K. So what I'm going to do is I'm going to assume some hidden variables that tells me if each of these variables is in or out of my model. So if it's 1, it's in the model. If it is not, it's not in the model. And I'm going to make those random variables basically part of my Bayesian analysis. All right, so what I'm going to do is I am going to try to construct a way that does not require me to compute basically and do Bayesian inference in 2 to the k models. Because if you really want to figure out what variables to select, you have to run calculations where this variable is in or is out, where this is in or out, totally 2 to the k. Rather than actually doing all these models, run all this Bayesian analysis for all of these models, we're actually going to sample in that space. And hopefully the way we sample, we will be sampling variables that are very highly probable based on the data that we selected. Okay? So, you know, the data basically tell us what is important and what is not, all right? And if we find the right posterior, will force us to collect, to converge basically towards the most probable models. All right, so this is the gamma variables. So let me do the following thing. I hear noise, I don't know, it's Friday, right? So the regression model, I am going to write it, this is our classical regression problem, where instead of having the design variables x and my regression coefficients beta, I plug in a subscript gamma there, and the subscript gamma goes over all the indices, all the inputs, and it tells me what part of the input variables are kept in this particular model. So this includes only the variables. When I put a subscript gamma there, right, it takes only some of the coefficients beta and some of the the design matrix X, and which ones does it take? The ones that defined by the coefficients gamma that they're equal to 1. All right? So I'm conditioning this likelihood model and say, if I knew which model will be in, then this is my likelihood for this gamma takes only the variables that are important in the analysis. Okay? All right. Remember, gamma now is a random variable, which we don't know which models are in and which models are out. All right. So given gamma, we know exactly what to do, right? I mean, you can take your G prior, any of the models we did. So if we knew what gamma is, we know what to do, okay, if we knew what gamma is. So let me just go directly to gamma. Look at the calculation here and tell me, can I compute the posterior of gamma? What do I need to compute? To do this formula, what do I have here? The posterior of gamma is what? What is this? What is this term? Is the marginal likelihood of y, right? Given gamma. All right? And this is the prior of gamma. And I'm going to take that all models are equally possible. So actually, P of gamma, you know what's going to be? 1 over 2 to the power k. A uniform distribution over all the models. Okay? Can we compute this marginal likelihood? Again, the same calculation we have seen hundreds of times. To calculate this, there is no beta, there is no regression coefficients, so you plug in beta and then you integrate it out. Okay? And by miracle, notice this calculation says given gamma. Given gamma, we know what to do, right? We have everything. We have the likelihood, we have the posteriors. So there is the final answer. This term that you need to calculate this posterior of gamma is given by this expression, where x gamma and beta gamma are parts of the beta coefficients and the design metrics that you keep defined on which gammas are equal to 1. Can you see in spirit what the idea is? You want the posterior of gamma, which is proportional to this marginal likelihood of y given gamma, and that you can compute it, okay? Given gamma, you know what to do, all right? That's the previous analysis. The only thing I plug in a gamma subscript to remind you that you have to keep only the variables implicated by gamma equal to 1. So we have a posterior on gamma. So what can you do with this posterior on gamma? The rest is basically the formulas I gave you, but you can rely to Mr. Gibbs, all right, who devised basically an algorithm to sample from a high dimensional distribution by effectively sampling through the conditional marginals. So basically the idea is actually, let me just give you the algorithm. If you want to take samples of from the posterior of gamma, what you can do is you can start taking samples from this marginal posterior, where you keep, so you take samples of gamma 1 and you keep samples of gamma 2, gamma k constant, whatever they are as you iterate through this. Then you take a sample of gamma 2, where gamma 1 is whatever you sample from here, gamma 3 is whatever you had, and you keep converging like that. And when this thing finds a stationary distribution for gamma, that gamma will be corresponding to the most probable models, the most probable coefficients in your model. Okay? Now, this actually is not as complicated as it looks, because each of these gammas take only 2 values, which 1 and 0. So really what you need to do is you need to compute this for gamma equal to 1 and gamma equal to 0. All right, so it's sort of a simple sampling from with probability p and probability 1 minus p for each of these. So if you do that, you can get these posterior distributions of the coefficients gamma corresponding to each possible model in your regression analysis, and it comes out. So remember, the gammas, if you take a sample of gamma, will give you the most probable model, and the most probable model is the model that involves the intercept, input 1, input 2, and input 4 and 5. The second most probable model is 0, 1, 2, 4, 5, 9, and you can see the corresponding actually posterior distributions. The posterior values basically corresponding to each of these models. Okay? Now, I believe in the program, the way that it was done is it actually goes through all the models or something, I don't know, spends 2 hours basically doing all 3 hours to do all the computations, but then it also does the Gibb sampling, and the Gibb sampling basically gives you the most probable model. Wouldn't you be happy if somebody tells you from the 10 input variables, you only need this, right? I mean, this is a simple problem, so Gibb sampling, that's another way to actually do model selection, okay? So, again, you can do wonderful things in the context of Bayesian analysis, but for now it's Friday. Basically, we have 1 minute to go. I have to blah blah, all right? I don't want to say anything. John, do you have anything to add? Happy Friday, all right, happy Friday at 90 degrees in September. When is that? What's September? 22nd, okay. So let me just, as I told you in the context of the homework, you will need to find the means to convince us that you put a substantial effort on this. And if you do, you will learn more than what you think you can learn, okay? In which way you do it is your business. Don't expect that we will be giving you the computer programs in the next homework. It's not going to happen again. But don't assume that simply by saying, oh, I ran it and this is what I get, what can I do? Everything is there. You know, that's something for you to address, okay? I need to have your abstracts before the end of the month, okay? And I know it's a very difficult thing to select an appropriate abstract, and please do not look on whatever is posted there and say, oh, okay, I have to put something like that. Innovate. Come something with probabilistic robotics, with, I don't know, anything you want to, with bridges, with earthquakes, with whatever, okay? But I need your abstracts, and it's good to have them early so we can maybe exchange ideas on the way. If you give me the abstract, it has to be on an HTML format exactly as we send it to you, okay? So that way I can post it right away. All right, so we have 3 lectures ahead. Have a nice weekend. Work hard in the homework, and I will see you Monday.